Well, welcome everybody. Hey, what's up, Karun?
Hey, I'm good. How are you?
Hey, I'm doing good. Hey, have you seen this movie, The Dark Knight?
So many times.
And what do you know about chaos?
Well, apart from what Joker is saying here, I've been reading about this ridiculously famous metaphor that explains chaos theory called butterfly effect. So the theory goes this way. The butterflies flying somewhere in Brazil area could lead to major catastrophe somewhere in Texas or US region. And it's time to save the world. Let's perform preemptive chaos attack on the butterflies. Well, that's not what I meant, but you seem to have something to talk about.
Yes, I do. Joker's interpretation of chaos, which I'm not going to read here, got me thinking. And your interpretation of chaos, which is a single butterfly flapping its wing causes disastrous event, got me thinking further. We're a team that is building a lot of platform-level services on a massive infrastructure, and all it takes is a single event to create a disastrous event which could impact our customers. So without any further delay, let's talk about chaos engineering for PCF.
Well, before we look into the problem statement, can you give us an overview about what we do, what is our team is into?
Sure. Okay. Well, obviously, we're from T-Mobile. You already know that. We're fondly called as platform engineering at T-Mobile. And what we do, in a nutshell, is we provide simple, secure, scalable services that are platform and infrastructure agnostic. What I really mean by there is we provide services on different layers of the stack. And you may have seen the level of abstraction here, starting off with infrastructure as a service, platform as a service, containers as a service. And we are a team that is focused on delivering capabilities on the PaaS and the CaaS layer, and moving full speed ahead on delivering services on the FaaS layer.
So what's the big fuss about it? Like nowadays, every company has infrastructure stack that contains container, platform as a service, and function as a service, right? What's the big deal about this and with the T-Mobile?
Big deal? Okay. Let's talk about big deal. If you don't know already, we're actually one of Pivotal's largest customer. And in terms of the big deal, I'd like to put a magnifying glass with some numbers out there. We're running around 30,000 containers, roughly around 500 active users. Last we checked, there was 1,800 total users on our platform that consume our service on a day-to-day basis, right? If that's not enough, let's talk about the applications running on the platform. 80% of the business-critical apps run on our platform, from middleware to customer-facing apps. We just finished our last week's iPhone launch event. Really, it was a huge success because of the applications running on the platform. And behind the scenes, this is a massive infrastructure upon which we're delivering capabilities, and we're moving full speed ahead on simplifying our services more further, having self-service tools available to our customers and making it more flexible for our consumers. So we're getting our customers and our business used to the agility. That's the big deal.
So it looks like that's a massive infrastructure. I'm sure it's not one data center, right? We have multiple data centers. Okay, I get this. Can you show something interesting?
Sure. What do you think this is?
I think you know this. For me, it looks like an abstract chaos.
Okay. What do you think that is?
Whoa. Blue chaos.
Okay. What do you think that is?
This one, still some gaps. I think incomplete chaos.
Okay. So here they are. So what you see on the left side is the famous Death Star diagram. And this is a snapshot around the 2010s here when Amazon was making a pivot to the microservice distributed architecture, right? They have 2,000 plus services today since the time, and God knows how much more they're working on. But the fact here is the services that we work on get released to the wild, and that's the world that they live in. Netflix is no stranger in this ecosystem. They've been a company that is massively investing on microservices and moving full speed ahead with the same architecture. We're no different either. We have such a radical investment and a pivot towards the cloud-native model, a lot of applications getting containerized. And here's a snapshot of what our ecosystem looks like.
So, wow, I think I know where you're heading, but can you please explain us, how is this relevant to the topic today?
Sure. Before I move on, there's one thing I want to just emphasize here, right? As engineers, we write services. Little do you know that your services live in this sort of ecosystem. So it's more of a survival of the fittest model, just like how we live on the earth. It's survival of the fittest. Similar thing applies to your system. So when you release your systems and when you don't validate assumptions that you make while building systems, they're going to bound to fail. So T-Mobile is all about the uncarrier strategy. We have a big emphasis on the digital transformation initiative. And part of our initiative there is provide the net new capabilities to our customers so we can focus on like the best customer experience, right? So one thing that we're internally doing is thinking about that the only thing that is constant in our life is not just change, but also failures. So we like to embrace failures, and failure is one thing that's inevitable. Okay?
Yep.
So,
wait. Is that you?
No, it's not me, man.
Okay.
It's not you either. We're not a mom and pop store that is going to run a data center like this, but my point here is emphasize on the kind of failures that could happen for the services we deliver on, right? So think about platform level failures for a second. Our data center is in different regions. Of course, one of our data centers is an earthquake prone region, which means disaster will happen at some point. How are we prepared for the disaster is the question here. Think about some of the assumptions our engineers make while building services. Network being homogeneous. We have infinite bandwidth. We have infinite compute storage resources, all of which is false. So how do you validate those so you can like protect yourself from these failures? Think about application failures. This is a unique case because we have 30,000 containers, 4,000 plus applications, which means that I would like to get to a point where we run targeted attacks on a specific application running within a container. And what happens to dependencies the applications reside on? If that goes down, what's the cascading effect going to look like?
Yeah, so T-Mobile is not a single application company. We have about, like rightly said, Ramesh, 4,000 applications running on our platform, sharing the common resources and the common underlying infrastructure. So which means we have independent applications running and not very interdependent. So I get this, so what you're saying is infrastructure failure or performing chaos engineering attack on the infrastructure may not solve the problem in all cases. So you need to have a very targeted application level attack, wherein if you're attacking an application which is running on the same Diego cell, should not impact the other application running on the same Diego cell, right? So that's okay. I get the point.
Yeah. So that's the problem statement here. So what I want to do here is have you fly off with this problem statement and come back with a proposal on how we can solve this problem statement, right? I want to put your creativity to work here. See, what are the tools that we can leverage out there from open source or building our own tool and getting to a point where we can like adopt some principles of chaos engineering.
Sounds good. So every dog has its day, right? So my dog is busy with keeping the Slack channel active, and I was working on the chaos engineering stuff. So we definitely do not want to reinvent the wheel, right? So we started looking at the solutions that are already available in the market, and that could be open source and commercial as well. So we started our journey with ChaosLemur. As you can see, the lemur here, it's an open source solution, but it can only perform killing of the virtual machines. So you have a cluster running, and if you want to go and randomly kill a virtual machine, use ChaosLemur. But however, it doesn't address killing a process, introducing latency into the system, introducing CPU and memory hog, and then most importantly, the second half of the problem statement, which Ramesh explained, is the application knowledge. So then we moved on to Gremlin.
And can I pause you there for a sec?
Yeah,
Tarun?
sure.
Isn't Gremlin a commercial offering?
Yes. So Gremlin in this mix is a commercial offering. One good thing they have is the control plane of Gremlin runs as a SaaS-based offering. So which means one less software for the ops team to worry about, right? So however, in our investigation, when we were evaluating Gremlin, the commercial offering, we could see that it scales well by performing killing virtual machines, kill process, latency, CPU memory, but still it's addressing only the platform level issue. It doesn't know about where your application is running inside the cluster, right? So that's a big deal for us. So we moved on to Turbulence, and again, Gremlin comes with a cost. And most importantly, in my recent conversation with Mr. Colton, the Gremlin CEO, it seems they've been trying to have some, in their roadmap, build a capability on the application knowledge as well. So it's soon to come, but the version that we have evaluated, we didn't see that happening. Then we moved on to Turbulence, an open source solution.
And here's another question I have. I'm looking at the capabilities that Turbulence gives from an open source. It feels like one could replace another, meaning Turbulence could replace Gremlin, or Gremlin could replace Turbulence.
That's a great question. So, but again, let's be fair. It's unfair to compare Turbulence and Gremlin, commercial offering of Gremlin. For me, the way I look at Gremlin is it gives me a single window console for not just Cloud Foundry, but also operating Kubernetes and also on AWS. Whereas Turbulence is more focused on Bosch generated virtual environment, so which is Cloud Foundry. So Gremlin, wins in that case, but if you as a developer want to enhance something on top of Gremlin, then you have to rely on that company. Whereas on the Turbulence, it's an open source solution, you are free to develop the capabilities.
Understood.
So again, Turbulence doesn't address the application knowledge. So we started thinking about building our own capability here. So again, we didn't want to reinvent everything, so we adapted something called Chaos Toolkit. So CTK is a nice orchestration that can sit on top of Gremlin and Turbulence and similar solutions. And it can orchestrate your chaos engineering attack, not just on the platform, but yes, we have built some drivers in order to get the application level attacks to work. But what we have done is we have 2 drivers created under CTK. The first driver is the driver for the Turbulence. And the second driver is a homegrown driver that can go find out where your application is running inside the cluster, find out what are the services dependent the app is dependent on, and then perform chaos engineering on the app. I have 2 demos. I'll be talking more about that.
It's awesome.
So let's talk about the first problem statement what Ramesh has brought up, infrastructure or the platform level chaos engineering. I'm sure we all are aware of this component diagram on the Cloud Foundry. So it's a lot of interaction that is happening between each component. So each component could be a virtual machine, or a combination of processes could be a virtual machine here, right? So at the platform level, what happens if rep process that is running inside the Digo cell goes down? So as we know, the rep process is mainly responsible for container lifecycle management on the Digo cell, right? So what happens if the rep process randomly goes off, right? So what happens to the containers running inside that? So that's one way of simulating the platform level failure. Another simulation that I can think of is think about applications with auto-scaling as a service enabled, right? As we know, auto-scaling service primarily depends on cloud controller before it can do a scaling at the application level, right? So it can scale up or scale down the application. So introduce some traffic to the application which has auto-scaling enabled, and then bring down the cloud controller and see how the application behaves, right? So that's classic 2 examples I have. And how we do that is via Turbulence. So this Turbulence has been given by a gentleman, I don't know his name, but CPP for life is his GitHub handle. I hope he's somewhere here. If he's here, can you wave? Okay, thank God he's not here. Okay, so we have 2 components in Turbulence, API server and the agent. So the API server is a BOSH deployment, and it is hosted on the Cloud Foundry, whereas the agent goes and sits in each of the virtual machine. It has got several features out of box, like killing a VM, killing process, stress, control network delay, firewall, and shutdown. So these are all the features that come with the open source solution of Turbulence. But when we were investigating this, we thought about introducing some more capability to perform more sophisticated attacks. So those are the ones that we highlighted. How to pause a process, what happens if a disk is corrupted, what happens if you are limiting the bandwidth to a Digo cell, like what happens if I'm limiting to 5% of the traffic going to a particular Digo cell, and reordering the packets, what happens, right? And then targeted blocking, duplication of the packets. So how would your system behave if there is a duplicate of the packets coming in, right? So that's the platform level attacks I'm going to talk about. And then this is the demo. So the way we will drive this demo is we will have 2 scenarios here. The first scenario is we'll block the traffic to, we'll actually pause a process. So we have a demo video. So the first scenario is pausing a process on the Digo cell. So I'm going to open the Chaos Toolkit definition file. It's a JSON file with title and the description. So in the Chaos Toolkit definition file, we have to provide the configuration information where your Turbulence API server is running, and then followed by the method. So here is the Turbulence API server which is running there. I have used BOSH Lite, a single box environment for performing platform level chaos attacks. So first, I'm going to see where my Turbulence API server is running. So I have an alias name called blite -d Turbulence. Turbulence is the deployment name. And you can see that there is a single instance of Turbulence API server running on this IP address. So let me go back and then show you the method. So the method typically has action, the name, it can be any name, and then the module and the function. The function is attack. Type is pause process. The process name is SSHD and timeout for 1 minute. What we are trying to do is we are going to block SSH connection to the Digo cell for about 1 minute. So first, before we do that, let's try to list all the VMs. You see the Digo cell running there. And then let's do an SSH onto Digo cell. It's pretty responsive, right? It's very quick, within no time. Then let's go back and perform the chaos attack on that particular Digo cell. So how we do that? We have a Python script via Chaos Toolkit. We're going to run this experiment called pause_process.json file. It's all open sourced. It's there. You can run this experiment, and it's going to show you what is a steady state hypothesis is, and then and finally it's going to say that experiment has the status is completed. Let's do an SSH again. As you can see, there is a brief pause, right? So if you could pause an SSH, you could very well pause even rep or any process running in that Digo cell. And this is a UI component to the turbulence. It shows you what is the process and how much time it took, what is overall thing happening inside that chaos attack. So now it got released, the log got released after 60 seconds. I'm going to SSH again and see that it's pretty responsive, right? So we successfully did a chaos engineering attack on one of our Digo cell by blocking a process called SSH, right? So I'll go into the next scenario. What happens if I kill a Digo cell, right? What happens to the containers running within that Digo cell? So again, we have another JSON experiment file with title and description here. It can be anything for that matter, and then a steady state hypothesis followed by configuration and then the method. The method here has a function called attack, and then the task type is kill. And then we are going to say where is the Digo cell running inside CF deployment and a limit to 1. You can also very well kill one particular Digo cell, any random Digo cell for that matter running in the cluster. So we ran the Chaos Toolkit script, and the experiment went through successfully. Let's try to list the VMs. There's only one Digo cell in our environment for now, and you can see the Digo cell is missing there. So that's how you kill the Digo cell. And then since it's a Bosch hosted Digo cell, the Bosch will bring that up after some time.
That's awesome. Very impressed to see the demo, actually. Very excited, more than impressed.
Yeah. So so that's the first half of the problem. Let's look at the second half of the problem. How do you perform application level chaos engineering? So before I move in there, right, do you have anything interesting? What happens in the ops world? What kind of customer requests do you get?
Okay. You said interesting in the ops world, right? Okay. I think it's good to start off with some sentiments we see in our Cloud Foundry Slack channel. So we have around 850 users on our Slack channel, and we have an open support model, which is all requests funneled through the centralized Slack channel, and then we take it onwards from that, right? So it's a unified customer journey. But it comes with a cost. So here are some of the experience we run into. First one is my app isn't picking up latest configurations. I like to call this bad karma. So your app's not working. My app isn't connecting to Cassandra. This is another classic use case we see. This is because you misbehaved with the Cassandra tree when they decommission your cluster. My app works locally, but not on PCF. This is because your app misbehaved or your team misbehaved. My app was working till yesterday, but not today. This is because they didn't make the payments to us, so it's not working. But this sums up everything. Hey, what the hell is wrong with the platform? We had an incident of this right around 1 o'clock today. It's like, is PCF working, right? This is like asking, when Amazon or Netflix is down, did the internet stop working? That's the reaction people have, right? And the same reaction people have on us, which is when things don't work, they start with us because we are very nice with them, but it comes with a cost. But this is a genuine problem because we like calling ourselves enablers, and what that means is we will get the customers, meaning our app teams, what they need, get out of the way, and trust that they'll do the rightful things within the platform, right? But trust is a very expensive word. So we've started thinking that just being enablers is not enough. So we need to start thinking about being enablers and guardians, which means how do we empower our teams with tools so they can do the rightful things within our platform and build better resilient applications? Because all of these are classic use cases which can be tested with failure injection.
Great. So some of these questions, I think the developers or the end users themselves can proactively work towards identifying what the root cause of the problem is. They can gain that kind of knowledge if we are empowering them with some kind of a toolkit which they could run it as a service and then perform chaos engineering attacks on their application, see bringing down Cassandra cluster on their own and see how the app behaves, right? So they don't need to look for so it's all about educating the customers. And I think CF app blocker, what I have as a next demo, I think it's going to answer your questions. So have you heard about cascading effect?
Yes, I have. It's a simple analogy where we have interdependent services, and when a dependent service fails, it triggers a chain reaction, and ultimately your customer gets the brunt of a bad experience.
Awesome. So no matter how cloud native your application is, no matter how well you design your application based on 12-factor design patterns, there's somewhere one of your microservice depends on another microservice so badly. So this case is no different. Like here, the concert web service microservice is dependent on weather microservice, whereas weather in this case is dependent on third-party application. So what happens if the connection between weather and third-party goes down, right? It's going to create a timeout. This concert will go down, and eventually again here concert again is dependent on database service. What happens if the database goes down, right? So all this put together, I call it as a cascading effect. So there is a bad reaction that happens, and the web application which client is actually talking to would go down, right? So that's a cascading effect.
Let me pause you here, Karun. I mean, platform as a service is like a self-driving car. Don't we get tools like Hystrix, also known as circuit breaker, that can protect the concert or weather service here?
Well, that's a great analogy. In fact, thanks for that, bringing that point, because the concert and weather service here, yes, Hystrix, circuit breaker needs to be implemented in that aspect. However, we are not saying the CF app blocker, what we have built here, is going to replace Hystrix circuit breaker. It is going to verify whether your circuit breaker is working or not. So these are solving different. They can complement each other, and they can both coexist in the ecosystem. So let's try to see how this application behaves in this Spring Cloud context, right? So here's the diagram I have, which talks about, let's say, for now, for the second, this gives a launch pad for the next demo. Assume there is weather service and the concert service both deployed or scheduled on the same Diego cell, right? And you can see there is a traffic flow between weather and concert, and then all the way through the Go router, and weather and concert service are dependent on MySQL database, which is a common database. Again, you see a lot of connections going from weather to config server, service discovery, and a Hystrix circuit breaker. In the ideal case, right, everything works this way, but it may so happen your concert service might have gone down, right? How do you simulate this today? All you need to do is you use some command line, CFCLI, and then go to the app and then stop it, right? What happens if the weather to the database connection goes down, right? So the traffic is blocked. So what I'm trying to say is these two microservices are sitting on the same Diego cell, but I need a control on what I want to do. For example, I want to block traffic going to the concert. I want to block traffic going from weather to the MySQL database without impacting the concert service connection going to the MySQL database. Let's look at the demo, how it goes. So how we do that, again, this is the new driver that I was talking about. We wrote this CF blocker as a Chaos Toolkit driver, and what it does is all you need to do is fill that experiment file and tell the Chaos Toolkit which application you want to perform the Chaos attack on. If you mention weather, and it finds out, it discovers where your application is running in the cluster. And then it also finds out what all services your application is dependent on, like in this case, config server, service discovery, circuit breaker, and MySQL database. Then it goes and blocks traffic both to the app as well as services bound to that particular app. So again, I have a technical issue, but yeah, that's. So this is the demo. Again, we'll have two scenarios. First scenario is simulating app failure, right? So let's block the traffic from one microservice to the MySQL database. So I have two apps here, Spring Music and Spring Music 2. Let's check if these URLs are working or not. So let's go to the browser. You can just open and then see that the Spring Music app pulls the data from MySQL database, and that's how you see the albums being listed there. So we have not done any changes to the app. It's just a plain simple Spring Boot app that talks to the MySQL database. And then let's see what is the backend database that these two apps are connected to. So you have MusicDB, service name and the p-mysql, and these two are the apps that are bound to the MusicDB. Let's look at the experiment file. All this stuff remains same: title, description, configuration information. However, we'll see something called probes. So you can probe, like, okay, if the URL is returning your 200 OK message or not. So the Chaos Toolkit will take care of this. And there is another probe we have written for the second music app. The important part here is the method aspect of it, and there is a rollback aspect of it. So in the method, the type is action, and the provider is block service. That's a function that we are going to use, and we are going to pause the connection from app to the MySQL for 60 seconds. And we provide all the arguments like where the app is running, org space app name and the service name. And then after 60 seconds, how do you unblock that particular service, right? Again, you provide all the details. So what we did is, in this definition file, we put together a block and unblock function. In the block, we explained, like, okay, where the app is running and what is the time, how long the app should be blocked. And after that, after 60 seconds, Chaos Toolkit will unblock the app, right? So again, I use Python scripting via CLI and then run my experiment file, which in this case is block service. So we have added verbose mode here. So this verbose can give you very detailed information about the logging, but for the demo sake, we'll leave it without verbose. So the Chaos Toolkit on the app blocker started. It started blocking traffic to MusicDB bound to Spring Music. So as you can see, the CF blocker found out the application was running in 3 containers because it is a 3 instance of an app. And then it started targeting MusicDB. So let's see if the MusicDB is fetching any data. It doesn't fetch any data. It's blank, right? So it's going to remain blank for 60 seconds. But the same app, another app running on the same DGO cell is fetching the data. Both these apps are bound to the MusicDB database, but first app is blocked for 60 seconds. So this is just to create a customer experience. So how would your web application react, like, if one of the service goes down, right? So we wait for some time and then go back and see that, okay, the experiment is still running, and yeah, you can see unblock has started, and you can see Spring Music is back into action after 60 seconds. So that's the first scenario. Let's look at the second scenario now. So in the second scenario, we are going to block traffic to one of the apps running on the DGO cell, right? So let's block traffic to Spring Music. They are bound to, so MySQL database, again, you can see the app is loading perfectly fine without any issues. Let's perform the block traffic chaos engineering attack on the app. Let's look at the definition file first. In the experiment file, you'll find the title, description all standard, configuration is standard again, steady state hypothesis, and then the method. So in this, we are going to use block traffic function, and we are going to pass arguments like org space and app name. We don't need to pass the service name here, right? So because we wanted to block traffic to the app. So let's run this experiment now. So it started. As you can see, it started blocking all traffic to Spring Music there. Let's give it a few seconds, and so there you go. There is a successful attack, and we see a 502 bad gateway, whereas Spring Music 2 running on the same DGO cell is still responsive, right?
This is great. You were able to bring down an app.
Yep.
And just validate the 502 behavior.
So those are the two scenarios that I wanted to touch base on the CF app blocker, and yeah.
So Karan, you already answered my next question here as to like, did we contribute a portion of this to the open source community? But if you didn't know, we're big on open source, and there's an actual open source team at T-Mobile. So our contributions are already live as the Chaos Toolkit Turbulence on opensource.t-mobile.com. So if you're interested in looking at the work we have, you're more than welcome. And you can also reach us for feedback. But on a closing note, these are some of the demo videos also, which are available on YouTube and the Turbulence PR. Let's talk about the next steps, right? Now that we have a framework built, I think we need to put this tool to work. So what I mean by that is we need to get to a point where we can start running some game days. Now that we have a base framework, which I call as the building blocks or the Lego blocks, we need to start productizing this internally at T-Mobile to a point where we can run continuous experiments with chaos engineering, right? So really the principles of chaos engineering advocate that you have to run your experiments continuously, graduate from running from lower environments to higher environments, and have targeted game days during which you run these experiments and look at the actual impact to your customers. So we need to get that to work. And more importantly, if we're able to advocate for building better services from a platform perspective, we should be able to sell on this to our app teams and have them run failure injection tests as part of their pipeline. Envision a world where you can actually run failure injection tests as part of your CI/CD, and good quality code gets pushed out to production. Okay. Closing note, this is actually our team. Few of the folks here who have special spots on the left and the right pane, we're either under the weather or we're not at the desk, but we're a small team. We're actually running this platform abstraction layer at T-Mobile. Today we're working on PCF and PKS, but that's our team. A lot of hard work has gone into all of this year in terms of expanding our footprint across multiple regions, multiple data centers. And we just cruised through our last iPhone launch, and we're buckling up for the XR iPhone launch event. 0 outages, knock on wood. So very proud of this team. A lot of hard work behind the scenes. I want to definitely call out the team here.
Where are you?
You don't see me? I'm right over here.
Oh, that's awesome.
Oh, we also have a special guest, Rob. I think he's somewhere over here. Yeah, Rob's our fantastic Pivotal partner. So kudos to Rob because we work with him hand in hand a lot. So, gentlemen, thank you for joining us today. If you have any questions, yes, sir. Yes, that is in Bothell. Bingo. We have some few members from Atlanta and New Jersey, but most of us are in Bothell.
So your team is on the provisioning and ordering side or on the infrastructure and telephony and backend?
No, we manage the platform.
So what is the
team.
question? Can you repeat the question?
The question is, are we on the telephony side or are we on the infrastructure side? Yes. No, we're not on the telephony side. We're actually, nicely segmented from them. We run the platform. App teams deploy their apps on our platform. Yes, there are mission-critical apps like ordering apps running on our platform. Yes.
And the picture you showed, the flow picture,
Uh-huh.
are those telephony calls or your calls?
No, those are actual microservices deployed on PCF and the dependency graph between those microservices. So it's just getting started, and it's called as the Death Star diagram. So it's a dependency graph to show how complicated the microservice world is.
Those are going across the globe.
No, they're not a globe.
Okay, so the question is, you wanted to know how that graph came out, right? So there are a lot of tools like App Dynamics, which can basically draw a Death Star diagram. It can show you the interaction between various microservices. So the one that we have shown you is coming straight away from the applications running on our platform. It's it's not a globe.
Yeah, it's not a globe. It's really to show the ecosystem of microservices and the tight knit between the microservices. So one service fails, it could impact multiple other services. So that's the key point on that slide.
Do we have any more questions? Or I think if you have any questions, let's take it offline. So we'll be here, hanging here. We would like to attend the next session too. So
okay, thank you guys.
Thank you.